Assalamu alaikum friends. I'm Taqdees A. Siddiqui with Computer Graphics, a course being offered for Bachelor's in Computer Science students by Virtual University, Government of Pakistan. This is our 17th lecture today. We have talked about some three-dimensional concepts, and today we are going to take them a little further and then walk into some interesting 3D transformations. So let's begin. Although we have talked about this before, but since we are at the subject, let's recap this again. A 3D point, a point in three-dimensional world, well, it's simply the same as in 2D, but only one dimension has been added, so a coordinate for the third axis gets added together to define a point in 3D. So a 3D point is similar to its 2D counterpart. We simply add an extra component, which is z, for the third axis or the third dimension. So the point can be expressed as P comprising of three coordinates, x, y, and z. And visually as well, we have seen this before. Any point in 3D coordinate system would be expressed using all the three coordinates. How far along x-axis we need to move in order to make it to that point, how far along y-axis we shall be moving, and how far along z-axis we would be moving. Origin is again typically 0, 0, 0. All three axes, if they got their values 0, we move to origin to have x equal to 0, y equal to 0, and z equal to 0. And as soon as we start moving away from it, we start getting non-zero values for these three. So in order to make it to a point x, y, z, we would be traveling along the three axes, x, y, and z. Now if we've got some 2 points in 3D and we need to measure the distance between them, how shall we do that? Let's assume that we've got one point with its coordinates as ax, ay, az, and the other one is bx, by, and bz. Then if we need to find out the distance between the 2 points, which could be endpoints of a line segment, or it could be some two independent points, and we need to find out what is the distance between the two, we'll be using the Pythagoras theorem. So the distance between points A and B can be calculated as the square root of dx square plus dy square plus dz square, where dx is the difference between x coordinates of the 2 points A and B. So we calculate dx to be ax minus bx, and similarly dy would be the difference between the y coordinates of the 2 points. So we calculate dy as ay minus by, and similarly dz would be calculated to be az minus bz. We have talked about this before, but let's recap this one as well. A few basic things that we did cover while talking about vectors. So definition of a 3D vector: like its 2D counterpart, a vector can be thought of in two ways. Either a point like xyz, or a line going from the origin, which is 0, 0, 0, to the point xyz. So we'll be making use of both concepts of vector. In order to measure the length of a vector, to calculate the length of any given vector, we can simply calculate the distance between the origin and the point at xyz. So we know point xyz, we want to calculate the length. The idea would be to calculate the distance between the 2 points using the same formula that we have already discussed. Between any 2 points, if you want to measure the distance, take one point to be point A, the other one to be point B. The method that we followed would be employed. अब यहाँ सिर्फ इतना होगा कि हमारा पहला पॉइंट जो है वो ऑरिजिन हो जाएगा, और दूसरा पॉइंट वुड बी आर डिजायर्ड XYZ वेक्टर. So length would be given as x, y, z minus 0, 0, 0. The two vectors would be subtracted, and we'll take the magnitude of it. So we can expand it as the square root of x minus 0 squared. X minus 0 times x minus 0 means x minus 0 squared. Add to it y minus 0 squared. Add to it z minus 0 squared. So effectively you can see we are talking about the difference between point A and point B. This is our desired vector. This is the origin, the difference between the two, and we are taking the magnitude in order to give the length. So x minus its counterpart 0 squared, add to it y minus its counterpart squared, and add to it z minus its counterpart squared. So effectively what we get is square root of x square plus y square plus z square, because naturally all values are being subtracted, 0 is being subtracted from all the values. Therefore x minus 0 gives us an x minus 0 another x into x is x square. So we have square root of x square plus y square plus z square, and that would give us the length or magnitude of the vector. Then there is a concept of the unit vector. A unit vector is one that has its magnitude or its length equal to 1. डायरेक्शन के बारे में हम बात नहीं करते, हम सिर्फ उसके मैग्नीट्यूड को देखते हैं. अगर मैग्नीट्यूड 1 है तो दैट इज नोन एज अ यूनिट वेक्टर. सो in 3D computer graphics we will be making use of these unit vectors. That is why we need to define them. At times we need to convert our given vectors into unit vectors as well. So as and when required we'll be doing that conversion business as well. We will be recapping how we convert any given vector into a unit vector. So although we have talked about this before as well, but we shall be going through that part again. So direction remains the same. We only make its length to be 1, and that serves as a unit vector. Now if we need to find unit vector for any given one, so we can simply do that by dividing each component of the vector by the length. Calculation of length अभी हमने देख ली किस तरह से करेंगे. So length हमने evaluate कर ली, उसके बाद हम वेक्टर के हर एक component को उस length factor से divide कर देते हैं. What we get is a unit vector. So if we have a point x, y, z serves as our vector, length calculation would be similarly done, square root of x square plus y square plus z square, which would be the distance from the origin. We'll start at 0, 0, 0 and we'll go to the point x, y, z. That distance would be measured as the length of the vector. In order to calculate the unit vector, we'll be taking each individual component x, y, and z and would be dividing it by this length. So unit vector will be defined as x over length, comma y over length, comma z over length, where length is the magnitude of the x, y, z vector. Now please note that if the vector is already a unit vector, then the length will be 1 and the new values will be the same as the old ones, because dividing anything by 1 is going to result in the same thing. So x over 1, y over 1, z over 1 would be actually resulting in the same x, y, z. So the process would be redundant if we try to convert that vector into unit vector, but it would not be harmful. It would leave us again with a unit vector. Now we talk about addition of vectors. If you've got 3D vectors and we need to add them together, the process would be pretty simple one. Vectors when get added together, they result in vectors. We have talked about this, but this time we are talking specifically with respect to a point and a vector. If we need to add them together, what would be the resultant? If we have a vector and we need to add a point to it, then we say that point dot x would be equal to point dot x plus vector dot x. So the x component of the point and the x component of the vector would get added together. So in this way, the vector's x component would be added to point's x component, and we'll be getting the modified point x component. Similarly, the y components of the two would be added together. So we say point dot y equals to point dot y plus vector dot y. So don't worry about the notation. Simply what we mean to say is that the x components of the point and the vector are being added together, and the resultant is being stored as the x component of point. Y components of the vector and the point are being added together, and the resultant is being stored as y component of the point. And similarly, the z components of the two, the vector and the point, are being added together to come up with the z component of the point. So that is being stored as the z component of the point. Thus we add vector to a point. What other operations are possible? We can add, we can subtract. When we are subtracting two points together, the resultant is a vector. And similarly, if we are adding 2 points together, still the resultant is a vector, because we can simply express that addition as subtraction of negative point. So point plus point can be expressed as point minus negative point. So that effectively gives us that point plus point, the same effect as point minus point. Therefore, when we are subtracting 2 points or adding them together, the resultant would always be a vector. And if we subtract a vector from another vector, the resultant would always be a vector. And if we add 2 vectors together, the resultant would still be a vector. And a point plus vector would always result in a point. Point minus vector can be always expressed as point plus minus vector or negative vector, and would always result in a point. Whenever we need to multiply a scalar, vector multiplication with a scalar is required, then scalar is something that has only got the magnitude, it hasn't got the direction. So the process is pretty simple. That scalar value simply gets multiplied by the components of the vector and gives us the resultant. So you can see that if you've got some vector with its components x, y, and z, the x component of the vector would be multiplied by the scalar, and the resultant would be stored back to the x component of the vector. Similarly for y and z. So x, y, and z components get multiplied by that scalar value, and the modified results are stored back to the x, y, and z components of that given vector. Let's take an example of the scalar multiplication. If we've got a vector of length 4 and we multiply it by 2.5, well, of course, the resultant would be a vector of length 10, and the direction would be the same as that of the original vector. So given vector का magnitude हमें पता था, that was 4, we needed to multiply it by a factor 2.5. So multiplication would only alter the magnitude, length को सिर्फ alter करेगा. 4 times 2.5, we got the resultant to be 10, so modified vector would have length 10. Direction is not altered in this process when we multiply a vector by a scalar. So direction जो original vector की थी वही रहेगी, सिर्फ magnitude जो है, that has been altered now from 4 to 10. What if the same vector of length 4 is now multiplied by minus 2.5? Instead of multiplying it by 2.5, now we multiply it by minus 2.5. So what we are going to get is a vector of length 10 again. Magnitude would not be changed. What would that minus do? Yes, it is going to invert the direction of the vector. So if we multiplied it by a non-negative value, we did not alter the direction. If we multiplied by a negative value, the magnitude is the same. 2.5 पहले था, अभी भी 2.5 से मल्टीप्लाई किया, लेकिन अब के वो वैल्यू चूंकि नेगेटिव थी, मैग्नीट्यूड या लेंथ तो 10 हो गई, डायरेक्शन उस माइनस की वजह से इन्वर्ट हो जाएगी. अगर ओरिजिनली वेक्टर की डायरेक्शन ईस्ट की तरफ थी तो अब वो वेस्ट की तरफ हो जाएगी. दैट ब्रिंग्स अस टू मल्टीप्लिकेशन ऑफ वेक्टर्स. And when we talk about multiplication, we know that we've got 2 different types of multiplications. So the one is known as dot product, and the other one is cross product. When we take dot product of 2 vectors, the resultant is always a scalar, whereas in case of cross product, the vectors get multiplied to result in a vector. So in case of dot product, we would only be dealing with the magnitude of the vectors. We probably would not be talking about the direction associated with each of them, because that would always yield a scalar value, and scalars don't have directions associated with them. They are only associated with vectors. So the dot product of two vectors A and B is defined by the formula A dot x times B dot x plus A dot y times B dot y plus A dot z times B dot z. So you can see the two vectors A and B get their x, y and z components multiplied with the counterparts and get added together to form one value. So पहले वेक्टर का x component और दूसरे वेक्टर का x component, इन दोनों को हम मल्टीप्लाई करते हैं, x coordinate multiplied together, add to it product of the y coordinates of the two vectors. So एक का y लीजिए, दूसरे की y value लीजिए, multiply कर दीजिए, add it to it, take the z values, multiply them, add to it, the sum of all the three, that would form the resultant scalar, which would be the resulting dot product of the two vectors. We have another definition of dot product. We can always define dot product as product of the magnitudes of the two, or in this case lengths of the two, times cosine of the angle between the two vectors. So we can say that dot product of vectors A and B can be stated to be magnitude of A times magnitude of B times cos of angle between the two. So if you've got two vectors A and B with angle theta that they are making with each other, then their dot product can be expressed as magnitude multiplied and multiplied by cosine of the angle theta between them. About cosine of theta and its properties, cosine of theta would be greater than 0 if theta is less than 90 degrees or is greater than 270 degrees. So whenever the two vectors are making an angle of less than 90 degrees with each other or greater than 270 degrees, then only cos of theta would be giving us a non-zero positive value, greater than 0 value. It would be giving us a negative value or a less than 0 value when theta is greater than 90 and less than 270. So if the angle made between the two vectors is in the range 90 to 270, both exclusive, इसमें 90 और 270 शामिल नहीं है, if the angle is greater than 90 degrees but is lesser than 270 degrees, then the cos of theta would give us a negative value or a less than 0 value. And it would be equal to 0 for theta equal to 90 or theta exactly equal to 270 degrees. So you can recall that when we talked about the dot products of vectors earlier on, we said that cos of theta is an important indicator in terms of knowing what could be the orientation of the two vectors with each other. उनका आपस में angle क्या बन रहा है उसके बारे में हम predict कर सकते हैं by taking the dot product in this fashion. So if we get a value which is less than 0, we know what angle range is possible, and when we get 0 as the output, we know that the two vectors are either making a 90 degrees angle with each other or 270 degrees angle with each other. So practically speaking, one way or the other, they would be orthogonal to each other. They would be having a right angle, because when we take the smaller angle, that would be 90 degrees. When we take the larger part of it, it would be 270. So practically speaking, they would be orthogonal to each other, and only then the dot product of two vectors would be equal to 0. Now if we have a point of view at a position px, py and pz, and we are looking along the vector vx, vy, vz, then about a point p x, y, z poised somewhere in the space, using the dot product we can tell whether this point would be visible from our point of view looking along the given vector or not. That's a good use of the dot product. So if we are given a direction of view, a point of view, and we have a point about which we need to find out whether it is visible from our given point of view or not, we can tell that, we can decide that using the dot product. Let us see how. Now, if you want to know that if point P is visible from the point of view or POV, or if P is behind that point of view and is not visible, what we can do is we can declare a point 3D type POV, our point of view, a vector 3D type POV dir, and a point 3D type test, and a vector 3D type vtest. Then we declare float type dot product, and we calculate vtest.x to be equal to x component or x coordinate of point of view POV minus x coordinate of test. We calculate vtest.y to be the difference of y coordinate of point of view and y coordinate of test, and similarly the z coordinate is calculated to be the difference of z coordinate of point of view and z coordinate of test. And now we take the dot product, we evaluate it to be vtest.x times point of view dir.x, add to it vtest.y times point of view dir.y plus vtest.z times point of view dir.z. If the resulting dot product is greater than 0, we know that the point is in front of the point of view. Else, if dot product is less than 0, that means that the point is behind the point of view. And otherwise, the third case, when dot product would be equal to 0, that would mean the point is orthogonal to the point of view direction. So making use of the cos of theta concept, we were able to distinguish and tell the position of any given point while looking from a specific point in a specific direction, whether it would be coming in its way and would be visible or not. If it would be in the way, would be visible, we get a value of the dot product greater than 0. If it would not be, it would be behind the point of view and would not be visible in that direction of view that we are looking, then the value would be less than 0. And if it would be equal to 0, that would mean that it is, the point is, from the point of view, it is at the right angle, is orthogonal to it. Now, if we have two vectors that we want to calculate the cross product for, how shall we do that? For two vectors A and B, if we need to take their cross product, that would be evaluated in this fashion, that in order to compute the x coordinate of the resulting vector, the y and z coordinates of the two vectors would be contributing. For calculation of the y coordinate, the z and x would be contributing, and similarly for calculation of the z coordinate, the x and y would join hands together. So we can see A cross B would be evaluated to be the y component of A, or y coordinate of A vector, times z coordinate of B minus z coordinate of A times y coordinate of B, and that would form one value which would be the x coordinate of the resulting vector. Similarly, A dot z times B dot x, z of A and x of B would be multiplied, and subtract from them the product of x of A and z of B. And for z coordinate, we take A dot x times B dot y and subtract from it A dot y times B dot x. And this formula actually came from this determinate, the order 3 matrix. We can explain it a little further. See, when we are talking about the cross product of the two vectors, we've got their x, y and z coordinates listed over here. From here, when we are talking about computing the x coordinate of the resulting vector, only this part of the word is taking care of this business, and we are doing cross multiplications. So this times this minus this times this, and that yields the x component. For y coordinate, you'll see that these a dot y and b dot y would not participate, and x and z coordinates of the two vectors would be participating. And similarly, for z coordinate, a dot z and b dot z would not be used, and instead only the x and y coordinates, they would be used together to come up with the resultant values for the resulting vector when we multiply the two vectors together for a cross product. Another way of looking at that cross product would be that magnitude of A times magnitude of B multiplied by sine of the angle between the two vectors. That would also give us cross product, where the theta is the angle between the two vectors. So if A and B are making an angle theta between them, we can express the cross product as magnitude of first vector times magnitude of second, or length of A times length of B multiplied by the sine of the angle between the two. Now we have a question. We have talked about vectors, we have talked about representations of points as vectors, but when we are talking about computer graphics, a static screen with some objects drawn on it, would that be an exciting view? Or would you be interested in moving things around and mimic some life on the screen? But definitely, moving things around, transforming them from one place to another, from one angle to another, from one size to another, that is what is going to make things exciting and interesting. And that is what takes us to the word of 3D transformations. So we are going to talk about some primitive 3D transformations, and we'll see how we can make use of translation, scaling, and rotation, along with some other transformations to bring some life to our screen. In general, transformation is the process of moving points in space. We are living in 3D world, and we have started transforming 3D objects now. So our transformations would be in the 3D coordinate system now. The types of transformations, just recapping them, we have seen 2D geometric transformations before. We talked about translation, rotation, scaling, reflection, and sharing, and all these would be covered for 3D transformations as well. So let's start with translation. Translation is used to move a point or a set of points linearly in space. We have talked about translation in 2D planes. Now we are going to extend it a step further to walk into 3D. So वहाँ पर आपने देखा था कि हमारे पास ट्रांसलेशन वेक्टर जो था that was comprising of two things, tx and ty, कि x के along कितनी ट्रांसलेशन चाहिए और y के along कितनी required है. But now we are going to add another dimension to it. z axis भी आ गया, so हमें बताना पड़ेगा कि हमें x के along कितना मूव करना है, y के along कितना मूव करना है और z के along कितना मूव करना है. So our translation distances now would be tx, ty, and tz. And similarly, if you've got a point P defined by x, y, and z coordinates, then after translation we are going to get P dash defined by x dash, y dash, and z dash. X dash is computed or calculated as x plus translation along x, or tx. Y dash is computed as y plus ty, or translation along y. And z dash is similarly calculated as z plus translation along z axis. Here tx, ty, tz, they are the translation distances, and together they form our translation vector tx, ty, tz. Now we've got x dash equals to x plus tx, y dash equals to y plus ty, and z dash equals to z plus tz. They can always be expressed as a single matrix equation, the way we have been doing that before. So where our P is the x, y, z vector, P dash is x dash, y dash, z dash vector, and T is tx, ty, tz vector, and the matrix equation would be p dash equals to p plus t. So that's all that we have to get. Simple positional addition gives us our desired results. So transformed x is given by the original x plus the tx, the x part of the translation vector. Similarly, transformed y is given by the original y plus ty, and transformed z is given as the original z plus the tz. Let's just elaborate on that with another example. If we want to move a point 3 meters east, minus 2 meters up, and 4 meters north, notice the interesting aspect of moving minus 2 meters up. What would be the steps involved if we want to take this translation along? We've got the point 3D defined to be point 0, 0, 0, vector 3D vector with the values that we might be requiring to translate. Then we adding vector to the point, we get point dot x is equal to point dot x plus vector dot x, point dot y equals to point dot y plus vector dot y, point dot z equals point dot z plus vector dot z, and finally what we have is a translated point. So typically here we are representing that distance with delta. So if delta x is the translation factor along x, so that gets added to the original x value, delta y gets added to the original y value, delta z gets added to the original z value, and that gives us the new transformed points coordinates x dash, y dash, and z dash. So if we are talking about drawing of some polygon, then we definitely can make use of this transformed or translated point, which could be our starting reference, and redraw that object again. That was the idea that we discussed when we were talking about 2D transformations as well, कि अगर हमें किसी भी ऑब्जेक्ट को ट्रांसफॉर्म करना हो तो ज़रूरी नहीं कि हम उसके हर एक पॉइंट को अलग अलग ट्रांसफॉर्म कर रहे हों. अगर हमने ट्रांसलेट करना है ऑब्जेक्ट को, हम उसका कोई एक रेफरेंस पॉइंट जिसके रेफरेंस से उसको ड्रॉ किया जाता है. फॉर इंस्टेंस अगर हम एक पॉलीगॉन की बात कर रहे हैं और वो पॉलीगॉन जो है उसका स्टार्टिंग पॉइंट जो है उसको हम ट्रांसलेट कर देते हैं और बाकी सारे उसके एजेस विद रेफरेंस टू दैट स्टार्टिंग पॉइंट ड्रॉ होने हैं, तो फिर हम सिंपली ये करेंगे कि एक पॉइंट को ट्रांसलेट करेंगे और उसके बाद उस पॉलीगॉन को दोबारा से ड्रॉ कर देंगे. टेक अ सिंपलर एग्जांपल, सर्कल के केस में हमने क्या क्या पैरामीटर्स लिए थे इन ऑर्डर टू बी एबल टू ड्रॉ अ सर्कल. हमने कहा था हमें सर्कल बता दीजिए कि सेंटर्ड कहाँ पे है और ये बता दीजिए कि उसका रेडियस कितना है. सो गिवन दीज टू थिंग्स, सो एक्स वाई कोऑर्डिनेट्स हमने लिए सेंटर के और रेडियस की वैल्यू ली और उसको ड्रॉ कर लिया. अगर उसको ट्रांसफॉर्म करना था, ट्रांसलेट करके किसी और जगह ले जाना था, तो हमने कहा जी कि हम सिर्फ उसका रेफरेंस पॉइंट जो कि सेंटर है उसको ट्रांसलेट कर लेते हैं, नई जगह जाके रेडियस आर का सर्कल दोबारा उस नए सेंटर के साथ ड्रॉ कर देंगे. सो सेम कैन बी डन ओवर हियर एज वेल. सो वी ट्रांसलेट वन पॉइंट, और अगर बाकी की पिक्चर उसके रेफरेंस से ड्रॉ होनी है तो वी सिंपली रीड्रॉ दैट पिक्चर एट दैट ट्रांसफॉर्म्ड लोकेशन, एट द न्यू लोकेशन. नाउ दैट ब्रिंग्स अस टू the next step, which is that of homogeneous coordinates. We did talk about homogeneous coordinates when we were talking about the 2D transformations, और उसमें हमने जो कॉन्सेप्ट इस्तेमाल किया था फॉर सिंप्लिसिटी, हमने ये कहा था कि हम जो h फैक्टर है उसको 1 रख लेते हैं ताकि हमारे पास जो कोऑर्डिनेट्स ट्रांसफॉर्म होकर आए होमोजीनियस फॉर्म में वो वैसे ही हों जैसे कि ओरिजिनल थे. बिकॉज जो होमोजीनियटी की रिक्वायरमेंट थी वो क्या थी कि हम कोई ऐसा पेयर बना सकें वैल्यूज का जिसके साथ हम एक तीसरी वैल्यू ऐड करें, अनेक्स करें, और ये ट्रिपल जो है वो इक्विवेलेंट हो जाए हमारे ओरिजिनल कपल के. सो अगर हमारा एक्स वाई कोऑर्डिनेट था वहां पे ओरिजिनल, उसके अगेंस्ट हमने होमोजीनियस कोऑर्डिनेट जो बनाए वो थे एक्स एच, वाई एच और एच, जिसमें एच वो वाला फैक्टर था जो कि डिवाइड अगर करें एक्स को उस एच के साथ तो जो रिजल्टिंग वैल्यू है वो हमें मिलती थी एज एक्स एच. अगर उस एच को वाई को एच से डिवाइड करें तो रिजल्टिंग वैल्यू हमें मिलती थी एज वाई एच. तो हमने ये कहा कि हम h को 1 रख लेते हैं. h को 1 रखने से हमें आसानी क्या हुई कि हमने x और y की वही वैल्यू जो ओरिजिनल थी उन्हीं को इस्तेमाल कर लिया होमोजीनियस कोऑर्डिनेट्स में भी. सो वही काम हम यहां भी करेंगे. वी आर गोइंग टू मेक यूज ऑफ द सेम h वैल्यू ओवर हियर. हम h को यहां पर भी 1 ही रखेंगे एज यूनिट. उसको रखने का हमें फायदा ये होगा कि हमारे ट्रिपल्स जो ओरिजिनली हैं एक्स वाई जी वो एक्स वाई जी ही रहेंगे, साथ में उनके एक 1 ऐड हो जाएगा. सो आर होमोजीनियस कोऑर्डिनेट्स वुड लुक लाइक x, y, z, 1. And those are the ones that we are going to make use of to express our homogeneous matrices. और coordinate system में homogeneity का concept add करके हम तमाम तरह की transformations को एक ही तरीके से करने के काबिल हो जाएंगे. So the way we manipulated this in 2D transformations, we'll be able to do the same in 3D as well. For the moment, we are going to take a look at only homogeneous coordinates for translation. So here we have the equation would be P dash equals to translation vector T, Tx, Ty, Tz times P. So we are having a product of these two matrices. Matrix representation को देखिए. अब यहाँ पर हमारे पास ट्रिपल्स की बजाय क्वाड्स की शक्ल में वैल्यूज आ रही हैं. P डैश के कोऑर्डिनेट्स जो हैं वो अब x डैश, y डैश, z डैश और 1 हैं. इसी तरह से P के कोऑर्डिनेट्स हैं उनको भी देखिए. टुवर्ड्स राइट एक्सट्रीम वी हैव x, y, z and 1. And similarly we've got the translation matrix in the middle, and this one is also using homogeneous coordinates. So the equation is P dash equals to the translation matrix times the original point P. And as I said, now we have the coordinates of the points P and P dash given as quads instead of triples. P is given as x, y, z and 1, and P dash is given as x dash, y dash, z dash and 1. The translation matrix, which is poised over here in the middle, being multiplied by the original point P, that is given as 1, 0, 0 Tx, Tx being the translation factor along x-axis. And similarly, the second row, 0, 1, 0 Ty, is giving us the translation factor along y-axis. And the third one is giving us 0, 0, 1 Tz, which is giving us translation factor along the z-axis. The last one is, of course, added because of the homogeneous coordinates being used in order to incorporate or take care of this part. Now, when these get multiplied, recall your concepts of the matrix multiplication. The first row, the top row, would get multiplied with this lone column, the column vector, and we are going to get the first value, which would be evaluated to be the x dash coordinate of point P dash. 1 multiplied by x added to 0 multiplied by y added to another 0 multiplied by z. So all we get from this would be x plus 0 plus 0, and this 1 would be multiplied by this tx, and we are going to get tx again. So the resultant of this process of multiplying this first row with this column vector would be x plus tx, which would form the value x dash and is in accordance with what we already discussed. Similarly, when we take the second row and multiply it by this column vector, what we are going to get is 0 times x plus 1 times y plus 0 times z. So from this part, what we get is x becomes 0, z becomes 0, we get only y, and we add to it ty times 1. So what we have is y plus ty, and that is what forms the value y dash. And similarly, we can evaluate for z dash, and z dash would be evaluated from here when the third row of this translation matrix is multiplied by this column vector for point P. 0 times x plus 0 times y plus 1 times z plus tz times 1. So effectively what we get is z plus tz, and that is what forms the value for z dash. And for the last one, this whole would be multiplied by this. So first 3 zeros multiplied by the x, y and z are going to yield 0. 1 into 1 is going to yield 1, and that would take place for that one. So ultimately, having evaluated this, we would have formed another column vector for P dash with the values, the first one corresponding to x dash, second one for y dash, and the third one for z dash. So having translated that point, we can move on and do whatever next step might be in our transformation. As I said, अगर हम किसी सर्कल की बात कर रहे हैं, उसके सेंटर की बात कर रहे हैं, तो अब हमें ट्रांसफॉर्म्ड सर्कल सेंटर मिल गया है. इस नए सेंटर के कोऑर्डिनेट्स को यूज कीजिए और सर्कल को दोबारा ड्रॉ कर लीजिए. अगर कोई ट्राइंगल है या कोई और पॉलीगॉन है मल्टीपल फेसेस वाली, जिसके लिए स्टार्टिंग रेफरेंस जरूरी है और उसके रिलेटिव बाकी तमाम वर्टिसेस जो हैं उसके वो ड्रॉ होने, तो उस सूरत में वी कैन मेक यूज ऑफ दैट स्टार्टिंग पॉइंट एंड रीड्रॉ द पिक्चर अगेन टू कम अप विद द ट्रांसफॉर्म्ड इमेज. सो यू आर लुकिंग एट what we are going to get after evaluation. So x dash would be x plus tx, y plus ty would be giving us the value for y dash, and z plus tz would be giving z dash, and finally the last component would be 1. So we are going to keep it to this point today. We'll just recap what we have talked about. We did some recapping of our basic concepts about the vectors, and we did say that we can have vectors in the form of a point, or it could be a distance from origin to that point with the direction associated with it. And whenever we have two vectors, we can perform multiple operations on them, and we saw how to add them together, how to have their differences. In order to calculate the length or magnitude of a vector, we said that we are going to subtract the individual coordinates of the 2 points from each other, and the resultant would be giving us the difference between the 2 points and would be giving us length of the given vector. And similarly, when we talked about products of vectors, we talked about the dot product, which always yields a scalar value, and we talked about the cross product, which always gives us a vector value. So हमने ये देखा कि जब हम डॉट प्रोडक्ट लेते हैं तो डॉट प्रोडक्ट एक स्केलर वैल्यू की शक्ल में आता है, लेकिन हमने ये भी देखा कि उसकी सिग्निफिकेंस क्या हो सकती है. बिकॉज ऑफ कॉस ऑफ थीटा बीइंग इन्वॉल्व्ड ओवर देयर, वी सॉ दैट वी कैन ऑलवेज टेल अबाउट द ओरिएंटेशन ऑफ द टू वेक्टर्स टुगेदर, जिनका हम डॉट प्रोडक्ट लेने जा रहे हों. और ये हम कह सकते हैं कि जब हमारे पास कोई से भी दो वेक्टर्स का डॉट प्रोडक्ट 0 के बराबर आता है, तो इसका मतलब यह है कि वो दोनों एक दूसरे के साथ 90 डिग्री का एंगल बना रहे हैं, या अगर आउटर साइड से देखिए लार्जर एंगल वुड बी 270 डिग्रीज. तो जब कभी भी दो वेक्टर्स ऑर्थोगोनल होंगे टू ईच अदर, देयर डॉट प्रोडक्ट वुड यील्ड 0, एंड अदर केसेस वी डिस्कस्ड व्हेन इट इज गोइंग टू गिव अस अ नॉन जीरो वैल्यू ग्रेटर देन 0 और लेसर देन 0, और फिर हमने देखा कि उनकी सिग्निफिकेंस क्या है. फिर हमने इस डॉट प्रोडक्ट को एक काइंड ऑफ अ ट्रिक किया, उसको इस्तेमाल किया. हमने ये देखा कि किस तरह से हम ये बता सकते हैं कि अगर कोई सा भी गिवन पॉइंट एक्स वाई जी हमारे पास मौजूद है और हम उसके बारे में ये देखना चाहते हैं कि फ्रॉम अ गिवन पॉइंट ऑफ व्यू लुकिंग इन अ स्पेसिफिक डायरेक्शन, क्या वो पॉइंट विजिबल है या नहीं, तो उसके लिए भी हमने डॉट प्रोडक्ट का सहारा लिया. एंड वी सॉ दैट इफ आवर डॉट प्रोडक्ट वाज रिजल्टिंग टू बी 0, that would have meant that the point of view in the direction of view, the way we are looking, is at 90 degrees angle to the point. And if we get a value greater than 0, we know that the point is visible from the point of view looking in the direction of view. And if we get a negative value or dot product yields a value less than 0, that means that the point would be behind our current point of view and would not be visible while we are looking in the direction of view. When we talked about cross products and their implementation, फिर हमने ये देखा कि क्रॉस प्रोडक्ट को साइन ऑफ एंगल बिटवीन द टू वेक्टर्स की टर्म्स में किस तरह से रिप्रेजेंट किया जा सकता है. वेक्टर्स ए और बी के हमने कहा कि हम मैग्नीट्यूड ऑफ ए टाइम्स मैग्नीट्यूड ऑफ बी टाइम्स साइन ऑफ थीटा के जरिए से भी क्रॉस प्रोडक्ट को रिप्रेजेंट कर सकते हैं. एंड दैट ब्रॉट अस टू द ट्रांसफॉर्मेशंस. फिर हमने ट्रांसफॉर्मेशंस की डिफरेंट टाइप्स जो हैं उनके बारे में बात की, और एक ट्रांसलेशन को लेके आज हम चले. और ट्रांसलेशन को पहले तो उसका बुनियादी कॉन्सेप्ट हमने देखा कि किस तरीके से हम किसी भी गिवन पॉइंट को जो कि 3 डायमेंशनल स्पेस में है उसको ट्रांसलेट कर सकते हैं. सो पॉइंट की ट्रांसलेशन समझने के बाद हमने इसको मैट्रिक्स की फॉर्म में रिप्रेजेंट किया. मैट्रिक्स रिप्रेजेंटेशन को इम्प्लीमेंटेशन स्पेसिफिक डिटेल्स उसकी देखने के बाद हमने होमोजीनियस कोऑर्डिनेट्स को इंट्रोड्यूस करवाया. और होमोजीनियस कोऑर्डिनेट्स का कॉन्सेप्ट वही वाला जो कि हमने 2D ज्योमेट्री के अंदर 2D ट्रांसफॉर्मेशंस के अंदर यूज किया था, उसी को हमने यहाँ पर एक स्टेप और एक्सटेंड कर दिया. हमने कहा कि वहाँ पर हमारे पास दो कोऑर्डिनेट्स थे x और y, तो x और y के साथ हमने 1 ऐड किया था एज द फैक्टर ऑफ होमोजीनिटी, और इसी तरह से आज हमने कहा कि x, y और z हैं तो उसके साथ हम चौथा फैक्टर ऐड कर देते हैं 1 का, और इस तरह से हमारा हर ट्रिपल अब एक क्वाड की शक्ल में रिप्रेजेंट हो गया, और हमारा पॉइंट P जो है उसके अब कोऑर्डिनेट्स बन गए x, y, z और 1 जब हम होमोजीनियस कोऑर्डिनेट्स की बात कर रहे थे. और फिर हमने देखा कि इन होमोजीनियस कोऑर्डिनेट्स को इस्तेमाल करते हुए ट्रांसलेशन किस तरह से मुमकिन है. ट्रांसलेशन मैट्रिक्स और ओरिजिनल पॉइंट मैट्रिक्स को मल्टीप्लाई करके रिजल्टेंट के अंदर हमें क्या वैल्यूज मिलती हैं, और उनको हमने देखा कि वो इफेक्टिवली वही हैं जो हमारा थ्योरेटिकल कॉन्सेप्ट था टू स्टार्ट विद. जब भी किसी पॉइंट को ट्रांसलेट करने जाते हैं तो हमने कहा कि हम ट्रांसलेशन फैक्टर्स x, y और z ले लेते हैं, tx, ty, tz, और इस मैट्रिक्स इंप्लीमेंटेशन से भी हमें रिजल्टेंट बिल्कुल वही मिलते हैं. सो अगर x डैश जो है वो ट्रांसफॉर्म्ड पॉइंट का x कोऑर्डिनेट है तो हम ये कहते हैं कि ये x डैश इज इक्वल टू x प्लस ट्रांसलेशन फैक्टर tx. उसी तरह से हमें मैट्रिक्स कैलकुलेशंस के बाद, मैट्रिक्स मल्टीप्लिकेशन के बाद भी हमें एग्जैक्टली यही वैल्यू मिलती है. और फिर y डैश की वैल्यू y प्लस ty और z डैश की वैल्यू z प्लस tz की शक्ल में हमें मिली, एंड दैट्स द वे वी कंप्लीटेड आवर ट्रांसलेशन. लेकिन अभी तक हमने ट्रांसलेशन की बात की है, अभी हमारे पास रोटेशन, स्केलिंग और शेयरिंग और रिफ्लेक्शन की ट्रांसफॉर्मेशंस बाकी हैं. रोटेशन इज गोइंग टू बी अनदर इंटरेस्टिंग थिंग टू टॉक अबाउट, बिकॉज जब हम इससे पहले बात कर रहे थे तो 2 डायमेंशनल ज्योमेट्री के अंदर तो रोटेशन एक ही प्लेन था, उसी के अंदर रोटेट होना था ऑब्जेक्ट को. लेकिन अब हमारे पास 3 डायमेंशनल स्पेस है. अब रोटेशन जो है उसका कॉन्सेप्ट बहुत ज्यादा डायनामिक हो गया है, बिकॉज वी विल बी टॉकिंग अबाउट रोटेशन ऑफ एन ऑब्जेक्ट around x-axis or around y-axis or around z-axis, and each one of them is going to have its own implications. So उनकी implementation को हम next time देखेंगे, and we will talk about scaling as well. Scaling के साथ साथ हम reflection और फिर sharing की भी बात करेंगे. So that would be handled next time inshallah. Before we leave, just a point to ponder. जब कभी भी कोई चीज़ ऐसी हो जाए जिसकी हमें तवक्को ना हो, अचानक, तो हमारे मुंह से एक हेस्टी वर्ड निकल जाता है फौरन. आई वोंट स्पेल इट बट यू नो व्हाट इट इज. आपने ग्लास पकड़ने के लिए हाथ बढ़ाया और ग्लास हाथ से गिर गया. यू से ओह, डू वी हैव एन ऑल्टरनेटिव फॉर दैट? दैट्स व्हाट आई वांटेड यू टू थिंक अबाउट. आई मीन, लेट्स फॉर अ मोमेंट think about what the word actually means. Maybe we'll think twice before using it again. मुझे एक छोटा सा वाक़या याद आ रहा है. My eldest brother works for a company in Saudi. They have their showrooms. शोरूम के अंदर बाहर लगा हुआ शीशा जो था इस किस्म का साफ हुआ था कि बाहर से आने वालों को पता नहीं चल रहा था कि ये शीशा है या गुजरने के लिए रास्ता खुला है. An elderly person, तकरीबन 65 या उससे भी ज्यादा उम्र के साहब होंगे, started walking through it. It was a heavy person. With force struck किए, ग्लास पैन टूटा और कुछ इस तरह से टूटा कि उनके हाथों पे आ गया. Heavy glass sheet जो टूटी हुई है, and it is cutting into his hands. And my brother heard him say something. Would you like to know what he said? He said, Hasbi Allah. Allah is enough for me. Allah suffices for me. And he was really moved. Look at the man, look at his age, look at the scene. A glass sheet, a pretty heavy glass sheet, cutting into his hands. They are bleeding, and the man is not saying what we say hastily. He says, Hasbi Allah. Let's finish over here. Hope to see you next time again, inshallah. Allah Hafiz.